Today, we're doing a deep dive into something pretty extraordinary and honestly quite terrifying. It's this paradox in nature.
Right.
We're looking at an organism that seems, well, unassuming. It actually helps keep huge forests healthy all over the world,
Vital even.
but it also carries this chemical weapon inside it. So
Oh.
potent. I mean, the statistic is staggering, isn't it? 90% of fatal mushroom poisonings worldwide.
That's the one, Amanita phalloides, the death cap.
And yeah, our sources really hammer home just how deadly it is. Eating just a small piece, sometimes just part of one cap,
Cantina.
it's often a fatal dose. And what makes this deep dive so fascinating, I think, is that biological irony you mentioned. It's a killer, a silent one, but survivors often say it tasted fine, even delicious sometimes.
Which is just wild. It starts this toxic countdown, takes days, maybe weeks, and then catastrophic liver failure.
Organ shutdown. So our mission today, really, is to get under the hood of this thing. Why is it so deadly? How did it spread everywhere? And this delayed toxin. Why is it so perfectly timed, almost maliciously so? And can we even do anything about it?
That's the core of it.
Okay, let's start with how it looks.
Yeah.
Because it's a master of disguise, right?
Or-
A real chameleon.
Totally. When it's mature, the cap size varies a lot. 4 centimeters, maybe up to 16. And the color, this is key.
Oh.
It's all over the place. Greenish yellow, sometimes olive brown, tan, occasionally even pure white.
It means it doesn't scream danger like, say, a brightly colored frog.
Exactly. No warning colors. And its shape changes, too. When it's young, it's like a little round button, sort of egg-shaped. Then as it gets older, it flattens out, becomes more convex.
And I read something about the smell changing, too. Like, young ones smell okay, but older ones, less so.
Yeah.
Yeah, there are accounts saying young ones smell wonderful, but they get, well, stinkier with age. But here's the crucial bit. The toxicity doesn't change. Young, old, greenish, brownish. It's deadly at every stage. Okay, so appearance is deceptive. Now, what about where it came from? Because the story there has really shifted, hasn't it?
Oh, massively. For decades, the assumption was, oh, it's everywhere, must be native, everywhere except maybe Antarctica. Just seemed logical because it was found on so many continents.
Oh, that wasn't right.
Not at all. DNA evidence blew that wide open. It turns out the death cap is fundamentally European, specifically native to Europe and the British Isles. That's its homeland.
So, how did this European mushroom become a global menace? North America, Australia, Asia?
It was basically a stowaway, a biological hitchhiker. It didn't spread its spores on the wind across oceans. No. It traveled hidden in the root systems of trees.
Wait, in the roots?
Yeah, European trees like oaks, elms, birches. When humans decided to transplant these trees across the world for forestry or landscaping...
They accidentally packed the death cap along for the ride.
Exactly. It was unintentionally spread by the very species it partners with, which brings us to that partnership.
The mycorrhizal relationship.
Ah!
Okay, let's unpack that because mycorrhizal sounds a bit technical.
Ah.
Is this a genuine partnership or is the fungus just, stealing from the tree?
No, it's absolutely a true symbiosis, a critical one, happening underground. So the fungus has these really fine thread-like structures called mycelium. Think of them like extra roots.
Okay.
It uses these mycelia to connect with the tree's actual roots. And yes, its main goal is to tap into the sugars that the tree produces through photosynthesis. That's its food source.
Right, so it is taking something.
It is. But, and this is a huge but, it gives back so much. That mycelial network acts like this vast extension of the tree's own root system. It's much better at reaching out into the soil and pulling up vital minerals.
Like what kind of minerals?
Things like phosphorus and nitrogen, which are often hard for the tree roots alone to access efficiently. The fungus absorbs these nutrients and feeds them directly to the tree.
Wow, so the tree actually benefits.
Significantly. Trees in these mycorrhizal partnerships are often much more resistant to drought, more resistant to diseases. The fungus literally makes the forest stronger, more resilient.
That's the paradox right there. It strengthens entire ecosystems, yet it holds this substance that's just incredibly lethal to us.
It really makes you wonder, evolutionarily speaking, why develop such a potent toxin? Maybe it was originally to deter insects or small animals from eating it. We can only really guess. But for us, the focus has to be on the toxin itself, alpha-amanitin.
Alpha-amanitin. Okay, this is where it gets medically serious because this is the primary killer toxin out of the few it produces. What exactly is it doing inside the human body?
Okay, think of alpha-amanitin as this tiny, incredibly precise saboteur. It goes straight for a crucial piece of machinery inside our cells, specifically liver cells. It targets an enzyme called RNA polymerase II.
RNA polymerase II. What does that do?
It's basically the cell's copy machine for DNA. It reads the genetic instructions in your DNA and transcribes them into RNA messages, which are then used to build all the proteins the cell needs to function, repair itself. Just love.
So alpha-amanitin jams the copy machine.
Perfect analogy. It binds tightly to RNA polymerase II and stops it from working. Dead stop. The cell can no longer make the essential proteins it needs. It basically starves itself from the inside out and undergoes apoptosis, programmed cell death.
Cellular suicide, essentially.
Pretty much.
Yep,
And
yep.
the really, really bad part? Alpha-amanitin is incredibly tough. It's heat stable.
Meaning, cooking doesn't help.
Meaning cooking does absolutely nothing to neutralize the poison. Boiling, frying, baking, doesn't matter. The toxin remains just as deadly.
Which leads us to this timeline. You called it twisted before, and it really seems designed for maximum damage before anyone knows what's truly happening. Walk us through that timeline.
Okay, so someone eats the mushroom. For the first, say, 6 to 12 hours, maybe even up to 24, nothing might happen. Or, more typically, you get the first wave, severe gastrointestinal distress, like a really bad stomach flu.
Exactly. Violent nausea, vomiting, terrible diarrhea, cramps. The body knows something is wrong and is trying desperately to expel it. It's a horrible phase.
But then, things seem to get better. This is the scary part, the honeymoon period.
This is the truly insidious part. After that initial violent sickness, the patient often starts to feel significantly better. Maybe for a day, maybe two. They think, phew, okay, dodged a bullet. It was just bad food poisoning.
But it's a complete illusion.
A deadly illusion. Because while they're feeling better, the alpha-amanitin that wasn't expelled is being quietly absorbed through the lining of the intestine. It enters the bloodstream and makes a beeline straight for the liver.
And that's where the real damage starts, unseen. Precisely. During this honeymoon, the toxin is binding to the RNA polymerase II in liver cell after liver cell, shutting them down. The damage is accumulating silently.
And then, after this false recovery, what happens? When the liver damage becomes obvious.
This is typically from about 24 hours up to a week after eating the mushroom. The liver starts to fail. Massively. We're talking about widespread liver cell death necrosis.
Which causes a cascade effect.
Yes. The failing liver can't do its job filtering toxins, regulating metabolism, so the kidneys start to fail. Toxins build up in the blood, potentially affecting the brain, leading to confusion, coma, and often, within about a week, death from multi-organ failure, primarily centered on the liver.
And that period of feeling okay is when they should be getting intensive care, but they might just be at home resting.
Which is tragic and why the fatality rate is so high. Early intervention is key, but the symptoms mislead you.
It makes sense why it's responsible for so many deaths now, and the main reason people eat it is they just don't know it's the death cap. Mistaken identity.
Almost always. It's rarely intentional. Remember that variable appearance. And the fact that it now grows under common trees all over the world, thanks to transplantation, it's a recipe for confusion.
People foraging for wild mushrooms.
Yeah, foragers mistake it for perfectly safe, edible mushrooms all the time, especially if they're foraging in a new country or region where the local lookalikes are different from what they're used to back home.
Can you give some examples? What does it get confused with?
Well, in North America, especially when it's young and button-like, it gets mixed up with edible puffball mushrooms. Very dangerous confusion.
Okay.
In Asia and among Asian communities foraging elsewhere, it's frequently mistaken for the paddy straw mushroom Vulvariella vulvacea. That one's cultivated, widely eaten, looks superficially similar, a really common, tragic mistake.
And more generally.
Globally, it often resembles mushrooms in the Agaricus genus. That's the family that gives us the common button mushrooms, field mushrooms you buy in the store. So if you're not an expert, not meticulously checking every feature, the potential for error is huge.
And the death cap isn't alone in being this dangerous within its family, is it? The Amanita genus has other killers.
Oh yes, it's a notorious family. Now, most people might picture Amanita muscaria, the classic red cap with white spots, the toadstool from fairy tales. That one's toxic, causes weird neurological effects, but it's rarely fatal and pretty hard to mistake for food.
Right. So who are the really dangerous relatives?
The ones to truly fear, alongside the death cap, are its cousins known collectively as the destroying angels.
Destroying angels. Sounds ominous.
They are. These are species like Amanita virosa, Amanita bisporigera, Amanita ocreata. They're known for their ghostly, pure white appearance. Ethereal, almost beautiful, but incredibly deadly.
Do they have the same toxin?
Alpha-amanitin.
Exactly the same toxin, same mechanism of action. And just like the death cap, a single cap of destroying angel can easily be a fatal dose. Their immature button forms also look like other harmless white mushrooms. They're just as sneaky, just as deadly in their own regions.
We should probably add, though, not all amanitas are bad, right? Some are edible. That's a fair point, yes. There are edible species like Amanita caesarea, Caesar's mushroom, prized in Europe, and others like Amanita calyptoderma on the west coast of North America. But given the deadly members of the family, you have to be absolutely certain of your identification. No room for error.
Okay, so let's get back to the toxin. If someone has eaten a death cap and this alpha-amanitin is heading to the liver, what can medicine actually do? You describe the toxin as sticky. That sounds bad for treatment options.
It is incredibly difficult. Sticky is a good way to put it. Once alpha-amanitin binds to that RNA polymerase II enzyme in the liver cells, there's really no known drug that can just pry it off and reverse the damage directly.
So what are the first steps in the hospital?
Well, early on, if you catch it within hours, aggressive treatment involves things like activated charcoal to try and absorb any toxin still in the gut, plus massive amounts of 5e fluids to try and flush the system and support the kidneys.
But that only works before it binds in the liver.
Mostly, yes. It's about minimizing the dose that reaches the liver. Once significant binding has occurred and the liver starts failing, the options become much more drastic.
Which is where liver transplants come in.
If the patient is otherwise stable enough to survive the surgery and a donor liver is available in time, yes. A liver transplant is often the only chance of survival once severe liver failure sets in. It's literally replacing the poisoned organ.
Wow. Are there any preventative drugs? I think I read about silymarin.
Yes. Silymarin, derived from milk thistle, is used. It seems to help by sort of coating the liver cells, making it harder for the amanitin to get inside and bind. But again, the timing is critical. You need to take it before significant amounts of toxin have entered the liver cells. The patient has to realize they've eaten a death cap very early on, often before that deceptive honeymoon period is over. So its practical use is limited.
It sounds pretty bleak.
Yeah.
But there's some newer research, right? A potential breakthrough using something already used in medicine.
This is the really hopeful part, yes. Recent research has identified a compound called indocyanine green, or ICG.
ICG, what's that normally used for?
It's actually an imaging dye. Doctors use it routinely during certain surgeries or diagnostic tests to visualize blood flow or tissue perfusion. It's already FDA approved, widely available.
And how might it help against death cap poison?
Early studies, mainly in cell cultures and animal models so far, suggest that ICG can somehow block the toxic effects of alpha-amanitin. The exact mechanism is still being worked out, but it seems to interfere with the toxin's ability to shut down those liver cells.
Even after ingestion?
That's the hope and the focus of the research, that it might be effective even after the toxin has started its journey, potentially offering a treatment window where currently there are very few options besides transplant.
So if this pans out in human trials, this could be huge, absolutely enormous. Think about it. Potentially preventing maybe 100 or more deaths globally each year from death cap poisoning, turning it from this desperate race against time, ending in organ failure or transplant, into something potentially treatable with an existing, safe medical dye. It's very exciting. Okay, so wrapping this up, the death cap is just this incredible example of nature's contradictions, isn't it? A fungus that literally helps build and sustain forests, making trees healthier.
Vital ecological partner.
Yet it carries this incredibly sophisticated, heat-stable toxin that kills humans with terrifying efficiency, using disguise, and that horrifying delayed reaction.
It's mastered the art of poisoning through patience. And that leads to, I think, the final thought we should leave people with.
Go on.
Well, remember, this mushroom and its toxin evolved in Europe in this balanced relationship with its native trees and environment. It wasn't a global killer then.
Right, it was contained.
It was human activity, our desire to move trees around the planet, for industry, for aesthetics that broke down those geographical barriers. We essentially unleashed it.
We gave it the opportunity to become the world's deadliest mushroom.
Exactly. Our actions in reshaping the environment inadvertently empowered this incredibly dangerous organism on a global scale. It really makes you pause and think. How often are our efforts to manage or change the natural world unintentionally creating new dangers or giving unexpected power to things we don't fully understand?